All right, this is EAPS536, Introduction to General Circulation in the Atmosphere. This is our first virtual lecture. I'm Professor Dan Chavas. This is spring 2020. The topic will be the Hadley cell, and the reading is from Vallis E. In chapter 11 shown here. So, like I said, we're going to go back to the big picture again. So we're going to have a little bit of review from the first couple weeks of class. Just want to remind you again, we're on this rotating sphere. And so there's really these simple external ingredients that give rise to all sorts of interesting circulations in our atmosphere. So again, we have what we call planetary thermodynamic forcing, which is really differential heating. So that's solar insolation gradients, first and foremost, that we get more sun at the lower latitudes than higher latitudes, more insolation. And then also surface variability in terms of land, as well as variability in atmospheric properties, so variability in radiative absorption and emission as well, that ultimately give rise to having our tropics be warmer than our poles. Then we also have a planetary dynamical forcing for variability, which is rotation itself, F, so that varies with latitude, as you now know well, from 0 at the equator to a peak at the pole, as well as what we call differential rotation, so variations of F with latitude, which you've learned now as beta being fundamental for things like Rossby waves. And so these few simple external ingredients generate many types of horizontal circulations. And so I want to animate this movie. This is from the NASA GEOS 5 computer model. It's a really beautiful one just to look at all the swirls and motions that exist in this is a modeled version of our atmosphere, but it's still quite a good representation. So the whites or the gray shading represents total precipitable water. So brighter whites are more column water vapor. So you can see again, most of the water vapor is in the tropics where it's warmest. And then the colors denote precipitation rate. So you can really see where air is rising and water is condensing out and forming droplets and precipitation. And so yeah, it's really amazing to see the swirls particularly jump out to you at middle and high latitudes. It's associated with Barretclinic instability and extratropical cyclones that we discussed in the last few weeks. There's a lot of other exciting things going on. So I want to zoom out because I really want to highlight first, there's really two dominant features that we really want to think about, at least as first order features for our atmosphere. Which is the jet stream, this kind of west to east in both hemispheres. I'm just showing it in the northern hemisphere. Kind of predominantly zonal flow in the upper troposphere. And then the Hadley cell, which is in the tropics, is this meridional overturning circulation. And so we're going to focus on the Hadley cell here. We'll be talking about both of these in a moment. And so as part of this, within the system is a range of other waves and circulations. You've gotten really introduced in depth to Kelvin and Rossby waves, for example, in the equatorial region. There's also the intertropical convergence zone there, which is really just the ascending part of the Hadley cell where there's lots of rain. You also have other circulations, the Madden-Julian oscillation and the Walker cell, and then the monsoon, which we'll talk about next. Tropical cyclones is something that we probably won't talk much about, but then in the mid-latitudes, the dominant kind of weather maker is extratropical cyclones, and then really associated with Rossby waves in the jet stream. And so extratropical cyclones being the instability of the jet stream that breaks down into these cyclones. So this is our bigger picture that I want to remind you of again. So additionally, I want to highlight a couple of key contrasts that I brought up at the beginning of the semester, but now it's good to come back to, is to think about, one is the tropics, which is weakly rotating. So again, F is relatively small, though gradients in F, beta, still exist and are really fundamental, versus the extratropics, which are strongly rotating. So F is very large relative to its meridional variations. It's also strongly stratified. And then waves versus overturning circulations. You now learned a ton about all the different types of waves. These require a dynamical restoring force in contrast to overturning circulations, which are coming back to today, the Hadley cell, the Walker cell, as principally a response to differential heating. So generally less dense fluids tend to rise. So again, let's zoom out now and think about this kind of cartoonish but very important simple conceptual diagram of key aspects of our general circulation. So again, you have the Hadley circulation at low latitudes, and so this up circulation that's up, poleward, downward, and then back equatorward near the surface. And then you have the northeasterly surface trades. You have surface westerlies and eddies. And then you have that upper level westerly jet stream. And so this is just kind of the simple cartoon view of things. We're going to dig into this a little bit more here. So we can look at this data as well. So this is going back to a plot from Hartman, chapter 6, showing you in the top is the meridional overturning stream function. So the x-axis is latitude, the y-axis is pressure decreasing. And so this is at the top panel is December, January, February, so northern hemisphere winter. And then in the June, July, August is southern hemisphere winter, northern hemisphere summer, and then the annual mean at the bottom, which looks at least a little bit more symmetric between the hemispheres. That's actually shifted. You'll notice it doesn't, the center of the rising motion does not occur, is actually shifted a little bit towards the northern hemisphere. So. And so some information's on the left again, so it's generally confined to the tropics and stronger in the winter hemisphere, and we call this a thermally direct overturning circulation, which just means warmer fluid is rising and colder fluid is sinking. So that's what we call thermally direct. It's converting potential energy to kinetic energy. Here's just another view of it with more colors if you want, if you prefer the Vallis views from chapter 11. Showing the H's stand for Hadley circulation, and then F's are the Ferrel cells. So the Hadley cell is really much stronger in terms of the mass. These are mass stream function contours, so the spacing indicates the rate of flow of mass going upwards, or either upwards and downwards, or northward or southward. And then the arrows give you a sense again of rising motion near the equator. So in this case, they've plotted the winter hemisphere. You can see the Hadley cell is much stronger than the summer hemisphere cell, and it extends much farther into the winter cell. So we'll come back to that a bit later. It's actually just to note the units there are in kilograms per second. So you're actually seeing, again, when we say mass stream function, it's literally the rate of transfer of mass. And it's an integrated quantity, so it gets up to the highest values as you move to higher values. That's telling you something about the total integrated mass being transported upwards or meridionally, upwards and downwards or meridionally. Okay, so we spent some time early on discussing how air motion transports energy, so heat and water vapor. And so one thing we didn't really get to spend much time on, it was just at the tail end of this lecture, was that it also transports angular momentums. These are really two very fundamental quantities that are conserved in the universe in general. And so that gives us properties or conservation laws that we can use to understand our atmosphere. So just a quick recap on angular momentum per unit mass. It's just the tangential velocity, so the absolute tangential speed times of some mass, you can say this black point here, times the radius from the axis of rotation. So, and that's a radius perpendicular to the axis of rotation in particular here. So it's just radius times rotating speed in a very simple sense, as units of meters squared per second, because it's per unit mass here. So there's a direct analog to that on the Earth, which is we can think of an angular momentum of an air parcel. And so it's exactly the same concept, but mathematically looks a little bit more complicated. And we define angular momentum as this equation shown here again, per unit mass. And so we can just break this down very easily. The diagram is shown on the left. Is your distance from the axis of rotation is the radius of the Earth times the cosine of latitude. So as you get closer to the move poleward, you're actually moving closer to the axis of rotation. And then the second term here is the absolute tangential speed. And so it has two different components to it. So in the first part, this omega a cosine of phi is the tangential speed of the Earth. So it's solid body rotation that you're moving, the Earth is rotating. And so you can translate that to a tangential speed at some distance from the axis of rotation. So that a cosine phi again is showing up, omega r. And then the zonal wind speed. So that's your flow, your relative motion, or motion relative to the Earth, which is to say the wind. And so what's really important here, and to highlight this, is this defines angular momentum as positive to be westerly, which means towards the east. So just as we say a positive zonal wind is westerly, we say that's positive because that's the direction of the Earth's rotation itself. So important is when we say angular momentum, we're really thinking of westerly angular momentum. So okay, and so we can also think about conservation of angular momentum, which is to say that m stays constant unless it's acted on by a torque. So if we think about, for example, the most common one is the figure skater pulling his or her arms inward and moving some of their mass, that's not a point mass, but some of their mass to a smaller radius, so closer into the axis of rotation, and as a result, you spin faster. So you're approximately conserving your angular momentum, assuming you're not scraping the ground too hard. And so this is something we can also think of analogously. So the mass is moved to smaller radius, so the skater spins faster. This is very analogous on Earth. So you can think about an air parcel moving from one latitude to another, meaning that they're going to move towards the axis of rotation. And so in particular for air above the boundary layer, so in the free troposphere, it's nearly inviscid, which is to say nearly frictionless flow. And so that just means that it nearly conserves its angular momentum as it moves. Whereas in the boundary layer, surface friction acts as a torque that weakens the zonal motion in either direction, actually, which we'll come back to. So what does that mean? As air moving poleward will be accelerated towards the east. So you'll develop an eastward flow, a westerly flow. And this is just the Coriolis force. So this is actually the zonal component of the Coriolis force is literally conservation of angular momentum. So and so what does it say? We can put a little bit more of a number to this. Is if, say, you start at the equator, this air parcel, where you have no zonal flow at all, so u equals 0, but you still have angular momentum because you're on a rotating Earth. And then you move poleward, and you get accelerated to the east in the rotating frame of reference. You develop a westerly wind speed. And this is just essentially going to create a westerly jet stream. So at a very basic level, this is creating a westerly jet stream. This is not necessarily the mid-latitude westerly jet stream, but for now, we'll just be general. You'd be creating a jet stream here. Okay, so we can put these now together, and this is a really nice schematic, actually, that I think is really helpful to understand all of kind of the global view of both the Hadley overturning circulation and the westerly jet stream on our planet. And so we're going to walk through this and talk about a bunch of different things in the schematic. So the x-axis here is latitude, and then the y-axis is just altitude. And this is actually a bit of a cartoon, but it's a really, really nice one. So first in blue is showing this Hadley cell overturning. So these, you can think of them as stream function contours, essentially, again. Where you have rising motion over the or in the vicinity of the equator. And so we'll get back to that. So that's the Hadley cell overturning in the blue contours. You'll notice the Ferrel cell, which is hard to see, is much weaker, is in this blue stippled contour here. So it's going in the opposite direction. So it's a thermally indirect circulation. And we'll talk about that a little bit more in a moment, or actually not a little bit later. And then the black contours are the zonal wind. So solid is westerly and dashed is easterly. So this is flow into or out of the page. So you really have to orient yourself for a moment here. And don't worry about the other colored arrows for the moment. So we're plotting both the overturning circulation and the zonal flow on one plot here. Okay, so let's talk about the Hadley cell here. So the first part is thinking about warm, moist air rising near the equator within the ITCZ, so the intertropical convergence zone. So much of the moisture is rained out within this ITCZ. So going back to the movie, you could see precipitation strongly confined to this kind of narrow band. Air then moves poleward while conserving its angular momentum. And so this result is, again, a westerly jet stream. So this is exactly what we just talked about. As you move poleward, you're going to gradually be accelerated eastward to generate a westerly jet stream. So formally, this is the subtropical jet stream that's typically merged with the mid-latitude jet stream, but there are other processes related to the extratropical eddies themselves that serve to also accelerate the mid-latitude jet stream, but they're often merged together. So You can still think of these to some extent as the same. And then next, the air gradually subsides in the descending region over the subtropics, and this suppresses convection and precipitation. So as a result, the subtropics are often deserts. And then the last step is that air returns equatorward near the surface. And so this is really important that you're near the surface, because that means that there is a frictional torque due to surface friction, and so angular momentum is not conserved. And in general, surface friction weakens the flow in either direction. And we'll come back to that. So the result is a weak easterly trade wind. So there's this asymmetry at low levels. You have surface friction, so the flow is actually pretty weak. And then in contrast, you develop a jet stream aloft. So because there's no friction there. And if you go back to your tank experiments, you actually did this in your tank and saw something very similar as well when you did your geostrophic adjustment experiments. Okay, so an important point here is that in the time mean and global mean, angular momentum balance must hold. So our entire atmosphere is not gradually being accelerated or decelerated with time. So there are places where there are accelerations and places where there are decelerations, and those are associated with sources and sinks of angular momentum, and globally, so integrated globally, those must balance out. So the sources have to equal the sinks. So what does that look like? So at the end of the day, we mentioned the free troposphere is generally inviscid. So there's not really sources and sinks of angular momentum within the free troposphere. We don't have external sources or sinks of angular momentum. There can be mixing within the atmosphere without question. But so at the end of the day, it's really about the surface. So we don't have lateral boundaries either. So you'll notice that near the equator, so in the deep tropics, you generally have easterly flow, and that acts as a source of angular momentum. So you have surface friction, so flow is going from east to west, and meaning the easterly trade winds. And surface friction is trying to slow that down. So it's trying to make it more westerly or closer to zero, or I should say less easterly. And so that is actually a source of angular momentum, of westerly angular momentum for the atmosphere, acting on those easterlies. And that must be balanced by, at higher latitudes where we have westerlies near the surface, surface friction acting on that westerly flow acts as a sink of angular momentum for the system. So these actually have to balance. So in the low latitudes, there's always angular momentum being added to the system. And then what happens is that angular momentum then is lifted high up into the atmosphere by the Hadley cell, and then transported poleward, so following the Hadley cell circulation. And then somehow there has to be a transport of angular momentum from in the vicinity of, say, the jet stream down to the surface and towards higher latitudes, where there is the ultimate sink of angular momentum there. And so something has to be doing that. So something has to move westerly angular momentum from the tropics at high altitude down to the surface in the extratropics. And so right here, the Eulerian mean circulation can't do it. If you just look at this, the Hadley cell is not doing that. Instead, it's not a mean flow. It's actually the eddies and the waves themselves that do this transport. So that's kind of why these arrows have waves in them, is that this is actually a residual effect of eddies and waves. We're going to come back to that. So this is really, really important. So this is globally thinking about angular momentum and what are its key sources and sinks. So why is this important? And this is just a bigger picture thing to highlight, is that the mean state depends on the transport of energy and angular momentum by circulations and eddies. However, so this picture here is the mean state. It depends on, we're saying there's a role to play for circulations and eddies. However, the properties of these circulations and eddies also depend on the mean state. So things like the PV gradient for Rossby waves, or the temperature gradient for Barretclinic instability. So this means that there's this mutual interaction, which is often referred to as eddy mean flow interaction, that is really, really fundamental to the system, to even the mean state, but it's really hard to deconvolve. So we'll be talking about that more later on. Okay, so now let's get back to the Hadley cell. So let's talk about Hadley cell theory, and we're going to start by just thinking about the primary focus is on the symmetric theory for the Hadley cell about the equator. So we're going to go back again to this idea of angular momentum conservation as you move poleward away from the equator. So the logic here is that as air moves poleward, the zonal wind, so U, increases with latitude. Since the near surface flow is weak because there's surface friction, this means that the vertical shear of the zonal wind also has to increase with latitude. And so at steady state, which is to say in thermal wind balance, which has to apply, the shear also has to have a meridional temperature gradient. We'll write d theta, d phi, so you can think about it in terms of potential temperature, just regular temperature. That has to also increase with latitude. So temperature gradients themselves are going to get stronger and stronger if you assume that this angular momentum solution holds. So what stops this from continuing all the way to the poles? So what, in other words, what sets the poleward edge of the Hadley cell? All right, so let's talk about this what we call an angular momentum conserving solution. So what that means is that whatever angular momentum you have at the equator is what you keep as you move poleward, again, aloft in the, think near the top of the troposphere, if you will. And so you can write in our equations for angular momentum as a function of latitude on the left side, and on the right side is just what you start with at the equator, so putting in phi equals 0, which is omega a squared. And what you can do is solve for u here, and this is what we call the angular momentum conserving solution for u as a function of latitude, which is given by omega a times the sine squared of latitude over cosine of latitude. Okay, and so what we can do then is pair that with thermal wind balance, which is shown here in spherical coordinates. So you can actually replace a d phi at the bottom with dy if you want to put it in terms of normal Cartesian coordinates, which is very similar. And so when you do that, you get a solution for the vertical mean potential temperature and how it decreases with latitude relative to the equator. So the theta of 0 is theta at the equator, and it decreases. And how quickly it decreases depends on the rotation rate of the planet, the radius of the planet, the latitude, as well as gravity and the depth of the troposphere there. So, and that's shown in the blue. The solution is shown again in blue on the right plot. So you can see how a temperature. Actually, this is shown just for temperature. I don't think it's fundamentally different for potential temperature. I'm just using that from the book. So you can see the angular momentum solution, conserving solution, starts off with temperature that's very, very flat over the first 10 degrees latitude. And then it starts to decrease much, much more rapidly as you go poleward of 20 and 30 degrees latitude. And so we'll talk about the red line in a moment here. So that's just the blue line. So we can have a simple solution, and so you can imagine this would also predict that it would get very, very cold as you go to higher latitudes if this were true. So what's interesting is, so this is where something that's called Held-Howe theory from Held and Howe 1980 is, so this blue line here, this is the same plot as before, is the angular momentum conserving solution. And the red line is basically what you would imagine if the atmosphere didn't move at all. So going back to the beginning of the semester, if we didn't have a Hadley cell, meaning you just had, so you had no horizontal motion, you just had radiative equilibrium, what would the temperatures of the average temperature look like? And so that's what that red line is shown here, and this is actually exactly what this form is debated still. So, but this is what Held and Howe came up with. And so what's interesting is, so there's a difference between the two curves, and so let's talk about that. But let's first think about the idea that we have this Hadley cell is that we have a poleward motion that's going, so we have motion going from the equator towards the pole that is going from warmer to colder temperatures. And so when you think about the concept of eddy heat transport, so if you wanted to think about a simple eddy heat transport term, it would be minus v prime dt prime dy. So you probably should have an overline, a bar on that. And so in this case, v prime we're saying is greater than 0. You have poleward motion. And then dt prime dy is less than 0. So you have it's getting colder as you go towards the poles. And so if you put those together, that's positive. So the minus sign up front makes this term positive. So there's a poleward heat transport. So air is moving from warm to cold. So it must be transporting heat with it fundamentally. And so that's what's shown in this pink arrow here now on the left, is that there's an idea, a really cool conceptual understanding of this is that, so our Hadley solution, if it's true, must transport heat polewards. And specifically what you're seeing here is that at low latitudes, the angular momentum conserving solution is actually colder than the radiative equilibrium solution, which is to say that the Hadley cell, in this case, implicitly has transported heat towards higher latitudes. So it's cooling the low latitudes. And then at high latitudes, the angular momentum conserving solution is warmer than the radiative equilibrium solution. And so that means this Hadley cell is causing warming. And so that heat can't come from nowhere. It has to be transported internally. And so this is really equivalent to saying there's a heat transport from these low latitudes to slightly higher latitudes. So from the deep tropics to the subtropics, if you will. And so what's really interesting, so putting this together, is just to say in a simple terms that this theory says that the Hadley cell strength depends on the difference between the temperatures of the angular momentum conserving and the radiative equilibrium solutions. So if the AMC solution was exactly the same as the radiative equilibrium solution, you wouldn't need a Hadley cell at all. It would just exist automatically. I would say the zonal jet stream associated with this temperature distribution would be perfectly in thermal wind balance, and you wouldn't need a Hadley cell at all. Okay, so what's pretty cool, so it's marked here on this pink is that there's clearly two crossing points of these curves. That's really important. So this theory is really great because it actually gives a thermodynamic constraint on the poleward edge of the Hadley cell, which is just conservation of energy. So the heat has to, if there's heat transfer, if it's going, it can't come from nowhere. It has to come, if it's going somewhere, it has to come from somewhere else. So we often say this is just an equal area argument in terms of the total heat removed from low latitude, so that area between the two curves up to about 12 degrees latitude has to equal the total heat added to high latitudes. So between about 12 degrees and then looks like something close to 30 degrees where that pink line is. And so that pink line really corresponds to what we call the latitude of the maximum latitude of the Hadley cell, or the poleward edge of the Hadley cell. And you can actually solve, assuming a specific form to that red curve, which is given in the book, you can actually solve for this poleward edge of the Hadley cell as a function of these parameters. Notably, the delta theta is the equator to pole temperature difference. And then again, gravity and the depth of the troposphere and rotation rate and planetary radius all show up, and even the kind of an average temperature theta naught. So this is really remarkable. So you can say something, make a prediction about what sets the polar edge of the Hadley cell. So this is one constraint. And so just to note, this theory predicts that the polar edge of the Hadley cell is around 30 degrees, which isn't too bad. So I should emphasize that the answer is actually pretty sensitive to the assumption of how quickly this theta bar RE, the radiative equilibrium solution, the red curve, decreases with latitude. And there's people who debate. It's actually not that straightforward to predict what that should look like. But it's still a beautiful theory and gives a very reasonable answer. So there's a second and alternative dynamical constraint that you can also invoke, which is Barretclinic instability. So we've just learned all about that. So you know it depends at the end of the day in large part on the horizontal or meridional temperature gradients, which give you vertical wind shears. So as we said, as you go poleward, the vertical wind shear starts increasing rapidly. And at some point, you cross a threshold where the system becomes baroclinically unstable, which is, again, going back to baroclinic instability. Your Rossby waves can interact, or even Rossby edge waves can interact and mutually amplify. And so the jet will break down into eddies. And so that's what's shown on the left here. The dashed line is, again, the angular momentum conserving solution for the zonal wind, which you can think of as a proxy for the wind shear. And then there's a baroclinic instability threshold that rapidly decreases as the wind shear is increasing, moving to poleward. And so that crossing point, you can actually solve a solution just given something that looks a little bit simpler, but it's actually similar in many of the parameters, the square root of NH over 2 omega A. And so in this case, that's about 20 degrees north or south here. So it's a little bit smaller, though that's there's also approximations put into, particularly with the static stability here. So the key thing is, at the end of the day, which is right? It's not really to say that either one is right or wrong. They're both constraints are probably important. The key thing to take away is that these both would have strong constraints on a Hadley cell extending any farther than something like 30 degrees north. So yeah, so we have two different ways of thinking about why the Hadley cell doesn't just go to the poles. And if you remember, we talked about the idea that if the Earth wasn't rotating at all, so you can actually look back at both of those equations, and if you said the Earth's rotation rate was 0, the Hadley cell maximum latitude should go to, I guess, to the poles. It might blow up. I'm not quite sure. I think in both cases they would just blow up if you set omega to 0. So at least that's consistent. Okay, so there's a couple of outstanding questions remaining that we won't go into too much detail on, but one is, why is it that the seasonal cycle of the Hadley cell is so strong? So we really just talked about this equatorially symmetric Hadley cell, but we know that the winter hemisphere Hadley cell is much, much stronger. So the side, so the Hadley cell has two sides to it, one on each side of the equator. And then on the winter hemisphere, the Hadley cell actually crosses the equator. So you can see in DJF on the top, the northern hemisphere is in winter, and you can see many, many red contours showing significantly larger mass transport and overturning that extends. It actually rises in the southern hemisphere and then extends well into the northern hemisphere in terms of the subsidence region. So and then similarly for June, July, August, that extends into the southern hemisphere. So why is that? And so what's nice is that the Held-Howe theory, this thermodynamic constraint, was actually built upon a little bit later. And so we can just go back to this. So the Held-Howe theory assumed that the peak temperature was right at the equator. So this is now showing in both directions how, so in the dashed line, is the radiative equilibrium solution. It's just normalized by the peak temperature, is now what's used for theta naught here. So the temperature is a peak at the equator and decreases, and then there's the angular momentum conserving solution is flatter near the equator, moving away from the equator, and then decreases more rapidly as higher latitudes. So again, we had said the thermodynamic constraint says that really the Hadley cell strength depends on the difference between the angular momentum conserving and radiative equilibrium solutions. So the areas between the curves. And so Lindzen and Howe in 1988 took the same theory and extended it and pointed out that if you assume that, so in the summer hemisphere, so with seasonality, the peak temperature is going to shift into the southern hemisphere. So all you have to do is think about shifting that kind of symmetric curve, in this case, northward into the summer hemisphere. And you can solve for the angular momentum conserving solution, assuming that you're starting not at the equator, but actually off equator. And so what you'll end up with is this black curve, which is shown, which now is not monotonic. It actually decreases as you go back towards the equator and then increases again. And so it's shown in this black curve. And so what's remarkable is that when you do this, you find that the area between the curves is now much larger in the winter hemisphere. So that means that there's significantly more heat transport done by the Hadley cell into the winter hemisphere. And so the Hadley cell is generally going to be much, much stronger. So this is something that the same theory can actually predict correctly, that the winter hemisphere should be much, much stronger. So it doesn't mean it's the only thing going on. But it's, again, very consistent with the theory, which is really, really nice. So it's, again, this is in Lindzen and Howe in 1988. And I'll post these papers in case you'd like to look at them. They're really seminal papers in our field. So just to finalize, it's just a figure from Lindzen and Howe in 1988 showing when you move the peak temperature from the equator, which is at the top, you get this, and this is in a numerical simulation, you get this nice symmetric Hadley cell, so same on both hemispheres. And then if you move it to 2 degrees north and then 6 degrees north, you'll notice that so again, that implies that the summer hemisphere is on the right. So you're moving the peak heating northward, and you're now getting a response that is a much stronger overturning Hadley cell that's ascending where the heating is peaked, but then now extending very strongly back into the southern hemisphere. So that's something just as a little teaser for that paper. So that's the Hadley cell, and I'm going to have a couple of questions on Blackboard for you to answer, so please do so. Thank you very much.